Спасибо, Валентин Николаевич. Ну, как уже Валентин Николаевич объявил, что надо переходить к научной части нашего семинара. И первым докладом научным, который будет сделан на этом мемориальном семинаре, будет доклад сэра Джона Мeuрига Томаса, который называется «Новые нанопористые Nanoparticle катализаторы». Так, что? Евгений Павлович. Я думаю... А? А вы не видите?
Gentlemen, I'm sorry about this delay. I do apologize for keeping you waiting. I have a mixture, a feeling of both pleasure and poignancy as a result of standing before you today. I was last in Novosibirsk 18 years ago, and I do recall the occasion extremely well. It was an occasion which I shall never forget for a variety of reasons. I am deeply indebted to chance, I suppose, that I got to know Kirill Zamaraev. It was in the Berlin International Congress of Catalysis in 1984 that we met. And I shall refer to that towards the end of my talk, because there is a particular message which I should like to convey. However, perhaps I should begin by explaining that when I was approached by the organizers of this very important event as to which lecture, which topic I should choose, I offered two titles, one of which was the unpredictability of science and its consequences, the other, Nanoporous and nanoparticle catalysts. Now, when I received about a week ago the list of speakers, which impressed me hugely, I began to think that it was more appropriate for me to speak predominantly on nanoporous and nanoparticle catalysts, because this is the theme that unites and harmonizes more appropriately the theme of this conference, in which you are looking at physical methods of examining catalysts at the molecular level. But I will, on the advice of the two very efficient secretaries who communicated with me in Cambridge, say a few things about the unpredictability of science. If time permits, I could very easily, in view of my recollections of Kirill, keep you here until midnight if you wanted me to, because there are so many things that come back to my memory. One of the joys of knowing Kirill was to know not only an outstanding scientist, but an outstanding human being, a man of tremendous intellect and great cultural breadth. In speaking to him, I would learn so much more about Dostoevsky and Tolstoy and so many other eminent Russian writers. One of my favorite authors is Chekhov, and almost every story that I had read, Kirill could elaborate on and give me deeper insight. But there's one incident that I would like to mention to you, which is a rather amusing one. In 1989, I was asked by the Science and Engineering Research Council in Britain, on which I served at the time, to organize a conference between scientists concerned with catalysis in the Soviet Union and their counterparts in Britain. And we met in Oxford. And Evgeny was there, and so were many others. Minachev was there, Krylov was there. And it was Kirill who led the Soviet delegation. Now, when we sat down in this room in Christ's College, Christchurch in Oxford, Kirill took me aside and said, "Will you tell all your English speakers to speak slowly, because we will have a little bit of difficulty in following what they say." So I did announce that, and every one of my friends nodded appropriately. And the first speaker, I introduced him, was Kirill. And as you know, Kirill spoke wonderful English. And as he gained in momentum, and the subject flowed from his mouth and his heart and his head, it was exhilarating to listen to it. The professor of physics at the Cavendish Laboratory in Cambridge, who was sitting behind me, tapped me on my shoulder and said, "Will you ask the speaker to speak more slowly?" So, this was so amusing that, well, I don't need to amplify it. Now, ladies and gentlemen, I want very quickly to run through what I have to say today. I could very easily take a great deal of time on this, but let me just explain why I believe nanoporous solids in particular and nanoparticles are highly relevant in this day and age. About a third of the periodic table, and I can't help looking next to Lomonosov, we have Mendeleev. Wonderful to think that the third of the elements in the periodic table, at least, can now be produced in microporous or mesoporous, or to use a general term, nanoporous form. By that I mean, you can so design them that the oxides of these elements predominantly, but sometimes the elements themselves, you can so design them by using structure directing agents when you form these materials, such that the diameter of the apertures or the cages or the channels that constitute these nanoporous materials, the diameter is controllable between a low value of about 0.35 nanometers, I usually talk in angstrom units, 3.5 angstrom units, right up to about 550 angstrom units, and it's controllable. Now that offers great opportunities for a variety of reasons. First of all, these materials have a huge surface area. Secondly, one can graft, one can anchor strange or heterogeneous atoms onto these inner surfaces so as to convert what is a high area solid, typically silica. Silica is so easy to produce in this form that you can generate an oxidation catalyst, a reduction catalyst, epoxidation, whatever, by inserting and grafting or anchoring, I use the terms synonymously, a heteroatom into that inner surface. Now also it means that because the materials are nanoporous, almost every atom in the solid, in the walls of the solid, and on the surface are indeed on the surface. They're accessible to any species that can diffuse into these pores. And of course, because the pore diameters are large, most species can diffuse. So you have, in a sense, all the techniques of solid-state science, solid-state physics, and solid-state chemistry. You can use diffraction, you can use spectroscopy, you can use computational science, you can use scattering, whatever. All the techniques that the solid-state physicist deploys are applicable in the study of the surfaces of these nanoporous solids. So that's a great advantage. In a way, these solids, which are continuous, a huge area, 800 meters squared per gram, thermally stable in the case of silica, to about 900 degrees centigrade, these solids are ideal and in a way are colloidal systems. If by a colloid you mean something, and this is the usual definition of a colloid, that has a very, very large area. Well now, that's what I begin by saying. Let me show you now a few examples. May I borrow a pointer? Is there a... This one. Ah, this is it. Thank you very much. Lasers look the same everywhere. Now, here is a mesoporous silica. The diameter here is about 100 angstrom units. The walls are very thin. And the walls are not very well structured. We know this from silicon 29 NMR. And we know also that they're pretty flexible. Here, if one were a Maxwell demon that had color vision, this is what one of these channels would look like. The white atoms are hydrogens, the reds are oxygens, the yellows are silicons. So there is an enormous number, a very high area, an enormous number of silanol groups. Now, here I show a typical electron micrograph using a technique of Rutherford scattering. We are using electron microscopy, but we scatter the electrons through a large angle. Not just ordinary Bragg scattering, which is what is conventional in so-called bright field electron microscopy. This is dark field, high angle, annular, dark field. Now, Rutherford showed that the intensity of a scattered electron from a nucleus of atomic number Z is proportional to the square of the atomic number Z. So therefore, if we have a relatively heavy atom, such as platinum or ruthenium or tin or whatever, palladium, most of the materials that are catalytically significant, if you have such an atom dispersed on a low Z substratum, like silica, then it stands out like the proverbial sore thumb. It stands out very, very readily. Here are these little particles, each of about 1 nanometer, 10 angstrom units in diameter at most. And if you have a cluster of ruthenium or platinum or ruthenium tin or ruthenium palladium constituting a diameter of about 1 nanometer, 98% or more of the atoms are at the surface. So you can see now, not only do we have a large surface area for the support, but we also have a large surface area for the nanoparticles. Now, I've shown here a drawing which is essentially interpreting this picture, this electron micrograph, which I also show at the back. The green colored atoms are ruthenium, and the blue are tin. And we know with absolute security of thought that the tin is anchored to the oxygen which is next to the silicon. How do we know that? Because we do X-ray absorption fine structure, one of the techniques that Zamaraeva used to great effect. So that is really a quick reminder of the kind of thing that we can do. If you take a microporous material where now you have the diameter much smaller, 5.5 angstrom units. In this case, it's not silica, it's aluminium phosphate, aluminium phosphorus oxygen 4, AlPO4. But you can readily substitute aluminium ions by iron or cobalt or nickel or manganese, whatever you wish, within reason. You can't, unfortunately, put copper in. If we put cobalt in the divalent state instead of aluminium, then in order to preserve electron neutrality, there has to be an acid functionality. This is the Brønsted proton. So this is an acid catalyst, and it catalyzes the decomposition of methanol to give you olefins. If, however, you oxidize this system, heat it, calcine it in oxygen, then the cobalt 2 becomes cobalt 3. And from XAFs, you can measure the precise distances. And now this is a most unusual environment. Most unusual environment. You have cobalt, you can also have manganese in a kind of tetrahedral arrangement. And it's in the 3 oxidation state, and that's a very good oxidation catalyst. Now, that is the kind of material, those are the kind of materials that we're talking about. I'm very quickly going to tell you some essential techniques, but I will gallop, I will go rather more rapidly, not quite as rapidly as Zamaraeva when he was in Oxford, but I shall go rapidly nevertheless through this. I just want to mention that it is a great advantage to be able to do simultaneous X-ray diffraction and X-ray absorption in situ under operating conditions. And also, one can do some electron microscopy ex situ, high-resolution transmission electron microscopy, high-resolution scanning transmission electron microscopy, electron energy loss, and tomography, which is a subject that is close to your heart in this institute, and which you pursue, I know, with great effect. Now, here is a typical XAFs setup. But it also enables us to do X-ray diffraction by being able to have a position-sensitive detector and a photodiode array. That's something we developed from 1988 onwards. And here's a typical setup in the Daresbury British synchrotron, with the synchrotron beam coming in here, the specimen is there. We can measure the X-ray diffraction pattern from this position-sensitive detector, and we can measure the X-ray absorption spectrum there. Now, I just want to tell you a brief story which we published in Nature in 1995. And it was done with deliberate intent, as it were, because we took titanosine dichloride, cyclopentadiene, which sandwiches a titanium atom. Now, when that is allowed to enter these channels, the mesoporous silica, I'm afraid it's not too clear here, you can, in the presence of an amine, draw away the chloride, and you end up by forming, not too distinctly, a half sandwich compound, one of the cyclopentadienes, with titanium underneath, sits there, and then if you oxidize this, you end up with a single catalytically active site. you use the cyclopentadiene as a means of ensuring that the titanium don't get too close to one another. So you generate a heterogeneous catalyst in which you have single sites. That's very important. Normally, homogeneous catalysts have single sites. Usually, heterogeneous catalysts do not. But with the advantage of this large area solid, you can produce single site heterogeneous catalysts. Here's the story in a rather more graphic way. Here's the half sandwich compound. And when we oxidize that, we produce this. Now, you might say, well, this isn't very much chemistry. This is not big news, you might say. After all, what you've shown us is titanium roughly in tetrahedral coordination with an OH group. But you know, up until the time when we did this work, which was in 1995, there was great dispute and a great deal of uncorroborated evidence to suggest that the active site in a titanium silica catalyst, and let me remind you, that is a commercially extremely important catalyst. The Shell company in the Netherlands produces megatons of propylene oxide using this catalyst, titanium on silica. And the accepted belief was that the titanium is dipodally anchored, two bonds coming from the titanium to the oxygens, and a titanyl, Ti double bond oxygen sticking out. That isn't the case. All the mechanisms that had been proposed for the epoxidation of olefins using that catalyst were based on a wrong assumption. They had the wrong picture for the active site. Now, computational chemists are wonderful people. I admire them hugely. One of the worries I have, and please don't misunderstand me when I say this, because some of my best friends are computational chemists, but they always get an answer, whereas I struggle experimentally, and I don't always get an answer. But a computational chemist always gets an answer. Therefore, it's very important that a computational chemist has the right model to begin with. And consequently, I emphasize this very simplistic fact, that that's the active site. Well, let's proceed. At steady state, when the olefin, cyclohexene for example, enters this active catalyst, at steady state, we can, by ersatz, using the kind of techniques that was very much in Kirill's mind over many years, we can work out that this is the environment around the titanium. There are 6 oxygens now at different distances. The figures in brackets are the ones that have been derived by density functional theory by my colleague in the Royal Institution, Richard Catlow. And I'm very glad that for 1 year of his life, one of your colleagues, Alex Shubin, joined Richard Catlow and myself, and with Kirill, the 4 of us had wonderful success in our work on the dehydration of butanols. But now this is the figure. Now, that enables us, let me quickly pass that, and I'm going to, because I'm going to be short of time, I'm going to pass that rather hurriedly, except that I want to show you how I introduce nanoparticles. I take a carbonylate, and since it's an anion, I put an organic cation in with it, and I can insert it into a mesopore. This is the electron diffraction, electron micrograph, and we can measure the ersatz spectra This is typical now of the kind of picture that you build up. The density functional theory then tells you precisely what the bond distances are when you have 12 rutheniums, 2 carbons and 4 coppers. Now that's an incidental point. Notice that by taking these minute nanoparticles, here I've got silica, nanoporous silica, with minute particles distributed within them. Let me show you what this business of high annular dark field, Z contrast imaging is all about. This is the microscope that we have in the old Cavendish laboratory at Cambridge, where my colleague Paul Midgley and I are working. The detector is here. This is made by a Dutch company known as Technine, the successor body to the Philips organization. Here's the lens configuration. Here's a bright field detector. This would be measuring Bragg scattering. Here's the sort of Rutherford detector, you see. And you notice what I've said earlier. So you can see how readily these particles stand out in the background. I will quickly pass through that. This is the principles of tomography spelled out in some detail, but I don't need to show you that, except you might be amused by this example of a bacterium, a magnetotactic bacterium. In most of the lakes and rivers and seas of the world, you have these bacteria which have a backbone of single crystals of magnetite. Each of these particles is a single crystal, and it's super paramagnetic. In an alignment of that kind, it forms a ferromagnetic entity. And that ferromagnetism enables the bacterium to follow the lines of magnetic force in the earth. And that's how it tunnels into the mud to retrieve its food. Now, we just wanted to show that as an example because there's a far more relevant picture when it comes to looking at a nanoparticle consisting of 12 atoms, 10 rutheniums and 2 platinums, inside this mesoporous silica. Now, we've color-coded the picture. Here are some of the nanoparticles. You see, we can take a zoom picture and look at each of these small nanoparticles. They're only 1 or 1.5 nanometers in diameter. We've made the walls sort of semi-transparent. So we can tell exactly what kind of catalyst distribution we have and where they are in the various pores, what the loading is, and indeed there's ample room, as you can see, for reactant gases to enter. Many of you were at the Innsbruck conference 9 months ago, and I showed this picture then. It's barely visible. There are 3 particles there. Each one of those particles is analyzed by X-ray emission, and one can see that the ratio of the ruthenium to platinum is, as we expected it to be, 5:1. And we are able to analyze each single nanoparticle. Now, mesoporous silica, in the way that it's been formed and prepared for the last 10 years as a result of work done in Japan, in Toyota Company, and in Waseda University, and also in the Mobile Company of America. These mesoporous materials, like the one I showed you a short while ago, they're very well ordered, but they are expensive to make, and they require a great deal of elaborate care to render them totally free of organic material. So commercially, if you want to industrialize a particular catalyst based on those so-called MCM silicas, it's going to be a very expensive job. It so happens there's a company in America, the W.R. Grace Company, division of it is known as Davison. For 100 years, they have been producing massive quantities of mesoporous silica. The only difference is that their silica is not ordered. It's not very well ordered channels. The channels go in all sorts of directions. But it's so cheap. It's $1,000 per ton. So that's very, very cheap. It's almost, you know, something that you can forget the cost. And that, if you want to industrialize, you know, the rules about catalysis. Remember, Kirill and I, we used to talk about this. Any catalyst has to be active, very active, as you can make it. It's got to be very selective. It's got to have durability, longevity. But it also has to have economic feasibility. It has to be relatively cheap to manufacture and also to be environmentally benign and so on. Now, if you look at this, you'll see this is the tomograph again of the mesoporous silica. Now we've put in the ruthenium-10, platinum-2, and they're inside the solid. So that's the beauty. Now, I'm going to go back now very quickly because I don't want to keep you for too long. Here are the titles of the various subdivisions that I could spend 5 or 10 minutes each upon, but I'm not going to. You'll be relieved to know. Single-site titanium-centered epoxidation catalyst. I am going to say something about that, because now, equipped with the information that we've been able to retrieve, we can postulate a very reliable mechanism for the epoxidation. And we can animate it. I'm not going to talk about single-site and enantioselective heterogeneous catalysts, although this is extremely important. One of my colleagues, a wonderful Indian gentleman named Robert Raja, he has been working with me for the last 6 years. And when we started carrying out these enantioselective reactions on mesoporous silica, the Bayer company in Germany were attracted by what we had done. And to cut a long story short, we collaborated with them for 2 years or so, and now they've patented many of the discoveries that we made. Of course, we don't know whether these will be commercialized, but they're likely to be. However, I won't have too much time to talk about that. I will say something about this. I'll say very little about that. I will say something about this because Professor Talsi, his work and his paper is of great interest to me. I'll say little about that and even less about the latter. So now, let's go quickly. Richard Catlow and myself and Dr. Sankar published this scheme. Here's the tetrahedrally coordinated, bare, pristine site, catalytically active site. In the active state, there are 6 oxygens, 3 at the bottom and 3 at the top, centering around the titanium. Now this is what we think happens, you see. Here comes the cyclohexene, and it plucks out an oxygen. See, that's the tetrahedral one. Then the peroxide comes in, and then the reagent comes in, and it plucks away an oxygen. This is a classic example of the Riedel-Ely mechanism mentioned in the textbooks on heterogeneous catalysis. You have the absorption of the peroxide, but the The olefin itself is not absorbed. So consequently, we can do that. Now, I don't have time to go into that. I do want to draw to your attention that these wonderful Italian friends, these people have been very clever in taking very quickly, not only can you have single-site titanium to do all those reactions, you can have single-site iron to do all these reactions, and many other single-site molybdenum or vanadium. Now, I'm going to canter very quickly, pretty as this may be. I just have too short a time. Now, I'm coming to the nanoparticle. Here's just one nanoparticle anchored inside a mesoporous silicon. Now, there's a lot of information on this slide. And what I'm showing you is hydrogenation of all these reagents, all these. And here are the products. Take, for example, muconic acid. Muconic acid can be produced from corn, from glucose, by biocatalysis, which we've done in the University of Michigan several years ago. So if you start with muconic acid and reduce it, you end up with adipic acid. Adipic acid is very important and of great interest to people in this audience. But you produce it not from benzene or cyclohexane and oxidizing that to give you cyclohexanol and cyclohexanone, etc. You do it from glucose. Many of these reagents are very important. For example, taking benzene to a cyclohexene gives you another method developed in Japan in the last 4 years of producing adipic acid. But I just want to show you on the next table, there's far too much information here, but there are two messages, only two, that you need to take note of. First of all these reactions down to there require no solvent. It's a solvent-free chemical reaction. And the less solvent that you use in this day and age, the better it is ecologically and environmentally. Secondly, there's an extremely high turnover frequency. Take this, for example. With this nanoparticle, the norbornadiene gives you 10 to the 5 turnovers per hour. That is so high that you can readily contemplate commercializing that kind of reaction. Here's the muconic acid again, which I just mentioned. This is what science, I didn't use that title, renewable nylons. Nylons are of no interest to me, but this is what the editor of Science magazine put down when they spotted our paper. This is a short excerpt from an article I wrote in Scientific American 13 years ago. I was talking about solid acid catalysts, and I'm going to say just a few words about them. One knows that there's an enormous quantity of mineral acid used petrochemically and chemically throughout the world. So much so that one day the public at large will protest. So much hydrofluoric acid, phosphoric acid, sulfuric acid, or mixtures thereof, are being used that it is damaging to the environment, especially if there's a spillage. In fact, some states in America 10 years ago banned hydrofluoric acid, but they lifted the ban because no substitute was found. People were looking for a solid acid which was just as strong as hydrofluoric acid for the alkylation of alkanes and alkenes to form high-octane gasoline, petrol. Anyway, I want simply to mention to you Here's a clay, a modified clay. For 15 years of my life, when I was at the University of Wales and then at Cambridge, I spent a great deal of time looking at modifying clays in order to make them very strongly acidic and in order to be able to prepare ethers, alcohols, esters, and so on. One reaction which we discovered, which is now the basis of a massive production source in Britain by the BP company, 250,000 tons of ethyl acetate are produced by the addition of acetic acid across the ethylenic double bond in the presence of an acid clay. Now, this is a very interesting, and you might think ordinary, but in fact it's a very important reaction. Almost all computer ink is dispersed in ethyl acetate. And ethyl acetate is a very important solvent, and it's biodegradable. Secondly, if you add the acetic acid to the ethylene, all the atoms end up in the desired product. It is 100% atom efficient. Well, we did take out a patent, or BP did. Now, I am no businessman. I sold this patent for £1. So, you know, if I were a smart businessman, I wouldn't have done that. But there it is. I've made no money whatsoever out of it. Not that one does science for money anyway. I want to show you an interesting slide. We heard from Professor Parmon today that Kirill started his career in Moscow. I started my career in a small town in Wales called Swansea. Now, it's a beautiful place. Here's Swansea University, where I was an undergraduate. This is where I was told about Mendeleev, all the great other Russian contributors to science and knowledge. Here's a solvent-free reaction being carried out by the professor of chemistry there now. But you know, sometimes when I show this slide, especially in America, I showed it in Caltech about a year ago, and half the audience were about to sleep. They weren't as kind as you are. I could see people dozing away. At that point I said, there is another reason for showing you this slide, because this is the town where Catherine Zeta-Jones was born. And everybody wakes up. So all the students laugh, and then the professors look at one another and say, who's Catherine Zeta-Jones? Now here's a reaction which we're very proud of. By taking a microporous solid, a zeolitic type of solid, in which the cages have an entry of only 3.8 angstrom units diameter. This is a half cage, and at the bottom of the cage is a cobalt in the 3-valent state. If you take an alkane, it can only enter like a rodent going into its burrow, nose first. It can only go that way. So, what happens is you can form, in the presence of a superabundance of oxygen, because oxygen can readily permeate this solid, you can get functionalization of the terminal methyl group. And that's a good method. Indeed, you can do it twice over and take linear hexane and form adipic acid from it. Now, here's the case where I believe I'm particularly interested in the talk that's to be given next by Professor Talsi. My students and I, my colleagues, particularly Robert Raja and Sankar, decided that we would put iron in the 3-valent state. We believe it's low spin, so it's D1. Into this iron aluminium phosphate number 5. We put cyclohexane in the presence of oxygen. And we can pick up cyclohexanol, cyclohexanone, and cyclohexane hydroperoxide. We can also pick up free radicals there. We know that there's a free radical reaction. Indeed, one of the reasons why, it was as a result of a conversation with Kirill, and it was a paper which I believe you and Kirill published in Journal of Molecular Catalysis in 1985, that I recalled that inevitably, if you have either cobalt-3 or iron-3 in homogeneous solution, and you bring in an alkane, you pluck out a hydrogen and you set off a series of free radical reactions. Now, we were interested in restricting the free radical to this local environment. Well, what is more, we deliberately decided to restrict the diameter by taking the same active site, but a smaller diameter. And look what then happened. Whereas we have three main products here in this ratio, now we have three main products with an enormous difference, and the reason is very simple. Here's the empty channel. Here's the cyclohexane going in. It can diffuse readily. The cyclohexyl hydroperoxide gets stuck there, but it's formed and some of it comes out. When it's converted to cyclohexanone, some of that comes out, and likewise for cyclohexanol. But when it's converted even further to a chain molecule, which is more sinuous, the adipic acid, that comes out more readily. So this is shape selectivity, governing the conversion of cyclohexane to adipic acid. Now, I'm going to stop there. I wanted to show you Robert Raja. He's half my age, but twice as able, I can tell you. So I'm delighted to be interacting with a young man of this kind. And before I finish, I want now to spend 5 minutes in talking about the unpredictability of science. I prepared that lecture, which is a 1-hour lecture, so please don't think I'm going to go through it all. I'll not. But in the course of that lecture, I talk about the element of chance. You know, as I told you earlier, it was because after I'd lectured in Berlin in June of 1984, 20 years ago, Gerhard Ertl of the Max Planck Institute, Fritz Haber Laboratory, put on a little dinner, a lunch, and 8 of us showed up, all the plenary speakers and 1 or 2 guests. And I had never met Kirill Zamaraev before, and it was my good fortune to sit next to him. And I can remember to this day when I said to him, little did I know at that time how expert he was in this field. We talked about the joy of chemistry, you know, in an honest sense, the joy of chemistry. There's a cultural, aesthetic, intellectual, as well as practical dimension to catalysis, but also to chemistry generally. I said to him, one of the things that really fascinated me as a student was to discover that there's this phenomenon of tunneling. Of course, I couldn't have chosen a more appropriate term, because Kirill then elaborated on all that he knew in a very gentle, very authoritative, and absolutely illuminating way. I just felt dazzled that this man could know so much about tunneling phenomena. Of course, he had studied it, and I heard him lecture on the subject much later. But it was the subject that really bonded us intellectually. Now, that was chance. Now, I want now to mention a really great chemist whom I know, Kirill Zamaraev, admired. And that chemist is my distant predecessor at the Royal Institution, Michael Faraday. Michael Faraday was one of the greatest experimental scientists of all time. I'm going to give this book to Ludmila. If I gave one to Kirill, you may have got one already, in which case I would ask you to give it to the Institute. But this is a book that I wrote on Michael Faraday when we were celebrating the 200th anniversary of his birth. He was born in 1791. Now, I know that when Kirill's father, a chemical engineer, discovered that his son was interested in science, he gave Kirill a book in Russian on Michael Faraday. And I have a slide which I didn't bring here, but I show it all over the world. And it's Michael Faraday in the Cyrillic script, which is wonderful, because that's what Kirill gave me. So now let me tell you just a few words about Michael Faraday. You know, he discovered so many things. He discovered benzene, discovered how to liquefy gases. He's the founder of magnetochemistry and photochemistry. But one of his greatest inventions was electromagnetic induction, the generation of electricity from magnetism. You know, wherever I go, especially if I fly by Aeroflot or by any other airline, and I come into a new city at night and I see the lights in the distance of people's homes, I think of Michael Faraday. And I think of the experiment that he did on August the 29th, 1831. He was 40 years of age. What did he do? He took a coil of wire with a meter attached to it, and he inserted a magnet, and he saw that there was a kick. And then he pulled out the magnet, and the kick went the other way. Now, that's the discovery of electromagnetic induction. Now here is a neodymium boride ferromagnet. It's very small, but it's a ferromagnet. And here is a coil with a light-emitting diode there and there. So if current goes this way, that will light up. If it goes that way, this will light up. So now we repeat Michael Faraday's experiment, you see? And there it is, the generation of electricity. It's converting muscle power, hydroelectric power, nuclear power to electricity. Now, Michael Faraday was a bookbinder's assistant. He left school at 13. He knew only arithmetic, reading, and writing. He was a voracious autodidact. He read everything that he had to bind. And when he was 21, a very friendly customer in the shop in London where Michael Faraday worked saw that this young man was a very intelligent man, said to him, "Would you like to go and listen to the last 4 lectures being given at the Royal Institution by Sir Humphrey Davy before he retires as director?" Humphrey Davy was only himself. That was in 1812, incidentally. The 1812. No Russian can forget 1812, I'm sure, right? Now, Faraday went along and sat in the gallery and listened, mesmerized, to the lecture and demonstrations given by the flamboyant and brilliant and absolutely coruscating wit of Humphrey Davy. Humphrey Davy combined brilliance of experimental science with great literary felicity. You know, he discovered the electric arc, he discovered sodium, potassium, calcium, magnesium, and strontium. He discovered cathodic protection. He did so many things. So Michael Faraday wrote to Humphrey Davy and said, "Do you have a job for me?" and the rest is history. Michael Faraday, when he wrote to him, sent a copy of the bound book of notes that he had written based on Davy's actual lectures. And Davy wrote back, and I must tell you, we have the letter still. Davy wrote back after receiving that fantastic document. He said, "I am far from displeased by the evidence that you give me." Only an Englishman can speak like that, you see. I am far from displeased. I speak not as an Englishman, but as a Welshman, right? I would have said, I am overjoyed. But the stiff upper lip Englishman says, I am far from displeased. Now, that was chance, therefore. We might not have heard of Michael Faraday, but for that customer going into that shop and taking and offering tickets to this young man to go and listen to Davy. And I now end with a quotation, I wish I could remember it all. When Kirill came to Cambridge with Ludmilla, and we had photographs taken, and you may remember we met the lecturer in Russian in King's College, Cambridge, and Kirill quoted Pushkin. In my obituary notice of Kirill in the London Independent newspaper, I gave the entire quotation. I have forgotten the details of it, but there is one element, there's one line in which Pushkin says that chance is that great creator. I would end on that note. Thank you very much.
Brilliant lectures taken with this completely understandable English. И я думаю, что на самом деле не время для вопросов сегодня, поэтому в программе у нас сейчас перерыв, если я правильно понимаю.
Coffee break.
Да. Кофе.
Okay,